Hello, welcome guys to this video series on neural networks. So over this video series, we're going to be taking a bit of a deeper dive into some of the fundamentals of neural networks, talking a bit more about the layers and components that they're composed of. But before we get into any of that good stuff, I thought it'd be a good idea if we started with a bit of a primer on neural networks. So in this video, we're going to be answering these two main questions. Firstly, what is a neural network? Secondly, what does it mean for a neural network to actually learn? So the first of these questions is a bit of a one marker in that, really put simply, a neural network is an approximation of some sort of target function. Okay, maybe it's not so simple, because what do we mean by that? Okay, so I have an example here. So imagine that you have some data, which is some sort of collection of, I'll call them x's and y's, where your y is somehow dependent on your x. So I've made this example here, where both x and y are real valued 3D vectors. Um, and you might, if you had a data collection like this, you might be wondering, okay, so I know my y's are dependent on x, but how are they dependent? Like, what is the mapping? What is the function that maps from x to y? Um, the example I've picked here is rather trivial in that it's obvious what a mapping is. It's literally the fact that x equals y, i.e. y equals x. And if we were to write that in a more canonical way, we would say that, f of x is ax plus b, but then a is just simply the identity matrix, and b will just be some zero valued vector. Very trivial. But unfortunately, the real world isn't so forgiving. So examples of real data might be, you might have a collection of images of some animals. That would be your X, and then Y's would be the labels telling you what animals in the picture. But of course, you can't just pick up a textbook and see that function written. It's not as trivial as this example. And then that's where neural networks come in. Because what they allow us to do is approximate some target function. So if we have a neural network and it's done its job well, on this data set, for example, our network might not come up with f exactly, but it will come up with some g of x, which we could write in the canonical form as c of x plus d. This will approximately be equal to f of x, by which we mean that c, once we look at our network parameters, will pretty much look like A, i.e. it will pretty much look like the identity matrix, and D will pretty much look like B, the zero vector as well. Um, so what do these things look like? Like, what is a neural network? So let's go back to our presentation. They look a bit like this. So we have our inputs fed in, and that leads to our output vector. So our input vector is fed in one index at a time. So our x0 will go into the first neuron, our x1 into the next one. So this network only has, the input vector would only be of size 2. In the example I showed earlier, they were all 3D vectors, but you get the idea. If we had another neuron in this input layer, then it'll take a 3D vector. So we describe them by layers. So the first layer is always the input layer, the last layer is the output layer, then all the stuff in the middle are called hidden layers. So the network is composed of these layers, and the layers themselves are composed of artificial neurons. So that's the circle things that I've shown you here. And each neuron can be characterized by a bias. We'll talk a bit more about that in a second. And between each layer, there is an associated weight matrix. And the weight matrix, each row of it is just a vector telling you all the weights associated with one neuron. So for example, this top neuron we have here with the first plus bias, all of its weights connecting to the input neurons will fall in the first row of the first weight matrix, and so on and so forth. So we just said that our network has these inputs and these outputs. We pass in the input as an input vector, and then the output comes out as a vector as well. And the ideal situation is that the output vector, so our y's, our y tilde, will match what the expected output is, i.e. y naught tilde would be close to y naught, y1 tilde would be close to y1. And that is the expected or ideal situation. So I've mentioned a bunch of terms here, weights, biases, but I haven't really spoken about what any of them mean yet. And there are a few other things that really we shouldn't be mentioning at this point. So associated with each layer is also an activation vector. So the activation vector will be a collection of all of the activations. So all, another word for that is outputs of each neuron, as well as um, the, there's also a bias vector for each layer, which is a collection of all of the biases for that layer of neurons. Yeah, but at this point, this is just jargon, really. So let's try and explain a bit more about some of the words that we have just used. And we should probably start with the name of this entire thing. So oftentimes you'll see a network presented like this, and it will be called a fully connected layer, fully connected neural network, or sometimes just called a multi-layer perceptron. What does that mean? So we can probably intuit what the multi-layer part is in reference to, since we just spoke about layers. But what is a perceptron? Um, well, a perceptron is a type of neuron that form the layers of the network, and it's governed by this equation. So we see f of x takes one of two values, 1 or 0. So that means the neuron will output either a 1 or 0. When it's a 1, it's activated. When it's a 0, it is not. And that output is dependent on the weighted sum of its inputs. So we take its weight vector, we do a vector product with that and the inputs from the previous layer, and then we add a bias term. And depending on whether that's greater than 0 or not, we either get a 1 or a 0. So ultimately, our neuron outputs something that looks like this step function here. But despite the name, in modern neural networks, you will actually never have a perceptron in a multi-layer perceptron. We have basically defenestrated the perceptron because of this problem here that I've circled. So as you can see, as you get z gets close to 0, where z is the weighted input, so wx plus b, that is just what we call z. When you get close to 0, any small change in that drives you all the way up to a 1 or pushes you all the way up to a 0, which is a bit of a problem if you imagine that, okay, so you have a network, you have passed in some inputs, look to the outputs are pretty close to what you expect for, I don't know, well over 50% of the examples that you've passed into the network. So you're thinking my network is doing a pretty good job, but it's not as good as I want it to be. So I know that if I change some weights just somewhere or some bias somewhere, I'd get a much better result. So you go ahead and do that. You will find that a small change in the weight could lead to a drastically different network output, which is obviously a problem, right? Because the ideal situation is that we change the weights a little bit and that nudges the output a little bit so we can gradually steer our network to producing the output that we want. But that doesn't happen with these guys. They also only take binary inputs, so that x vector can only be a vector of 1s and 0s, which of course is also a bit of an issue. So nowadays, neurons that you would see in networks will probably be more like this, which is a sigmoid neuron. So in a multi-layer perceptron, ironically, the neurons are actually sigmoids, not perceptrons. And they follow this equation. It looks a bit like the perceptron, but you don't have this discontinuity around 0 anymore, but this smooth incline. But now the good thing is if we change the input a little bit around z equals naught, the neuron output changes only a little bit, meaning that the overall network changes only a little bit, which is very important um, and allows us to actually learn. So we've actually accidentally answered our second question here, which is what does it mean for a network to learn? Um, it is that process that I just referred to, right? So we want our outputs to tend closer to some sort of desired output. Um, and so what we end up doing is changing our weights and or our biases to get our network to produce the outputs that we want. And the whole process of learning is really to continuously pass in these inputs, compare them with the outputs with the expected outputs, and then using some what we call a learning algorithm to update the weights till they are optimized. So right now I've just said a bunch of things again. Um, Lots of things unanswered, but this was just like a sort of intro talk. In the next video, we'll try and tackle a lot of these unanswered questions. For starters, we'll talk more about the parameters, what they look like, and we'll try to build a mathematical framework to deal with the parameters of the network. We'll also introduce this idea of a learning algorithm using a famous example called the stochastic gradient descent. We'll talk about how it works and how it can be used to train our network. See you next time.